And we're going to start with chapter 22, which is all about electrical forces and electrical charges. Electricity is very important because it's essential to life as we know it. It powers all of our electrical tools, all of our smartphones, all of our computers. It also powers your brains, powers your neurons inside of your brain, allows your nerves to pass electrical signals between themselves. So electricity is all over us, all over the world. And we're going to start our study of electricity with electrostatic forces. And we'll begin our study of electrostatics in the Greek times, with Greek scientists who would take amber, they would rub it with fur, and they'd observe sparks. You can observe this yourself. If you rub your feet, say you're wearing socks and you rub your feet along a carpeted floor and then you touch a doorknob or you touch a roommate, you'll see sparks. This is something we should be familiar with, something called static electricity. And it happens because you're building up charge on yourself. And something you'll notice, when you're building up this charge to get your static electricity, and you want to shock your roommate with it, the amount of charge you get is important, but also the distance you get from your roommate is important too. And these two aspects of static electricity, charge and distance, combine to give us something called the electric force. So what exactly is the electric force? Well, I've already mentioned it depends on charge and it depends on distance. So let's talk about charge first, since I think we have a pretty good idea of what distance means. Charge is going to be some quantity that describes how much electricity you kind of store on something. And it's based on something we call a fundamental charge. Our modern understanding of electricity builds up everything into terms of this thing called a fundamental charge. And that fundamental charge is the charge on the smallest part of the atom that you're probably aware of, something called the electron. And the electron has a charge which we denote with the letter Q, and that's equal to negative 1.6 times 10 to the negative 19 coulombs. And this is the fundamental charge in nature. All other charges are some multiple of this fundamental electron charge. You also have things called protons. Protons have a charge as well. Proton charges are very similar to electron charges. They have a charge Q, but protons are positive, so they have a positive 1.6 times 10 to the negative 19 coulombs of charge. Again, notice, it's a multiple of this fundamental charge. And sometimes you might see this fundamental charge written as E, charge of an electron equal 1.6 times 10 to the negative 19 coulombs, the fundamental charge in nature. We'll notice a couple things about the fundamental charges. First, the electron. The fundamental charge of the electron is negative. Fundamental charge of a proton is positive. They have the same magnitude but opposite sign. And something we know about signs for electricity, we know opposite signs attract. You might have heard the little saying opposites attract. It comes from this aspect of electricity, that positive and negative charges attract each other. And let's say you have an object comprised of many charges. The net charge in any object, the net charge is equal to the sum of the individual charges. So this is something you deal with in chemistry quite a bit, in atomic physics, where if you look at an atom, any old atom that you get on the periodic table, typically the number of protons is going to be equal to the number of electrons. And since they both have equal and opposite charges, the net charge in most atoms, when I sum up all of the proton charges and all of the electron charges, they cancel each other out. So the net charge in a typical atom is going to be zero. It's going to be what we call neutral. Sometimes you have atoms and they lose electrons. They lose electrons, so that means their net charge is going to become more positive. They're getting rid of electrons, so they're losing some negative charge, so the net charge is going to be some positive number, a little bit more positive. This is what we call a positive ion. Any atom that has some kind of charge we call an ion. If they lose electrons, it becomes more positive, so it's a positive ion. However, we can also have an atom that gains electrons. If it gains electrons, the net charge is going to become more negative. So it's no longer a neutral atom. We have a few more electrons than protons, so we become a little bit more negative. We call this a negative ion. And those are most of the basics that we need in order to start understanding and quantifying this quality of electricity called the electric force. And we quantify electric force through a gentleman's law known as Coulomb's law. And remember, Coulomb was the unit of electric charge. And what Coulomb's law tells us is the electrical force between two charges. The force between two charges is equal to this constant K times Q prime, one charge, times Q, another charge, divided by R squared, where R is the distance between the charges. So this is the general formula for calculating the magnitude of the electric force. K is something called the Coulomb constant. Look up this number in a book. You don't need to memorize this. But you might want to memorize, you might want to know what K is in terms of a more fundamental constant. K is also equal to 1 divided by 4 times pi times this letter called epsilon naught, where epsilon naught is something called a permittivity constant. And this permittivity constant is a fundamental constant. Again, we don't need to know this. You'll be given the number K anytime you need to solve something, or you can look it up in a book. Now, force, from Coulomb's law, F equals KQQ over R squared, just gives me the magnitude. To find the direction of a force, I need to make use of what I know about charges and how they interact. Direction of a force depends on the sign of both charges. if the charges are oppositely signed. So if I have a positive charge and a negative charge, then the force will be attractive. This is kind of like gravity. Gravitational force is always attractive. However, if I have two objects with the same sign, then the force is going to be repulsive. Two charges that are the same sign end up with a repulsive force. So opposites attract, like charges, same charges repel. And that lets you get the direction for the electric force. Two things to look into as you're studying up on electric forces. I would look at checkup 22.2, and also to learn about superposition of forces, you should look at page 706 and read about the problem-solving strategies, problem-solving techniques, and read specifically about the superposition of electric forces. It's similar to a material that we already learned in Physics 1 on how to add forces together. It's just applied to electric forces. So you should be able to read and understand this on your own time. If you don't, then send questions, and I can discuss this in class. And remember, you need to send questions 2 days before we're covering material in class. This semester is a little bit more difficult than last semester. We're moving at a fast pace again, so you really need to stay on top of things, and you can't fall behind one bit. Now let's discuss a few aspects of charge and charged particles. I've already mentioned this, but one of the most important aspects of charge is that every charge out there is a multiple of the fundamental charge. It's some kind of multiple of that electron or proton charge. So you can have an object that's not charged at all. That's going to have a charge of 0 times the fundamental electric charge. You can have a positive and negative electron charge, fundamental charge. You can have positive or negative 2 times the fundamental charge, positive or negative 3 times the fundamental charge. Always some kind of integer multiple of the fundamental charge. We call this quantization of charge. Charge always exists in some discrete multiple of this fundamental charge E. Remember that E is equal to 1.6 times 10 to the negative 19 coulombs. And because charge is quantized, this means that charge before something happens, some kind of chemical reaction maybe, all the charge before a reaction is equal to all the charge after. Charge does not disappear. And finally, we'll cover a little bit of stuff about moving charges, a little primer on moving charges that we'll go into more detail later on. There's different kinds of objects that you can have. And in particular for electricity, we want to talk about an object that's called a conductor. And a conductor is some kind of object that lets charge move easily. Easily move charge if you're on some kind of conductor. We're familiar with this. We'll do a couple demonstrations in class with this, but generally you think of conductors as metal objects, something that'll let electricity flow through it very well. And the way conductors work, they work on an atomic level. In a conductor, the electrons in the outer shells are loosely bound. So they can move. They can be stripped away. They can move. They're mobile. So electrons will flow around on the surface of a conductor. And furthermore, on a conductor, electrons tend to evenly spread out along a surface. These are two very useful aspects of conductors, and we make use of these quite often. And it turns out you have different kinds of objects that can make good conductors. You can have liquids. Liquids that conduct electricity very, very well. Liquids that are good conductors are ones that have lots of ions inside of them. So they have charged atoms inside of their liquid. Water is an example of a good conductor. It has lots of ions. These liquids that are good conductors, they're called electrolytes. So something like Gatorade, when it says that it's filled with electrolytes, that means that it has lots of charged ions inside of it. The chemical makeup of Gatorade is charged very, very well. It has lots of ions, and these ions move very well through the liquid. So it promotes the flow of electricity because electrolytes, ions, make good conductors. So Gatorade is actually a conductor. We also can have gases that are good conductors. If a gas is a good conductor, we give that a special name as well. We call these plasmas. And the best example of a gas being ionized is when you have a thunderstorm. Let's say you have a rain cloud. A rain cloud charges up the air that's around it. This charged air gets very, very ionized so that charges can flow. So the rain cloud ionizes air. And it lets charge flow very, very nicely. And if these charges flow, that's when you get lightning. So that's charges inside of the air, inside of the ionized air flowing. This is what gives us our plasma, our charged gas. And it turns out that these charges inside of the air, they really, really like to accumulate at points. They like pointy places. And you can get this kind of, you can observe this kind of effect when you have something called a lightning rod. Charges in the ionized air are attracted to the pointy tip of a lightning rod. And you can actually see the charges at a point in this ionized gassy plasma air because they glow. And they glow in something called a coronal discharge. And we'll attempt to show you a demonstration of this in class as well. We'll try to see and observe this lightning rod effect, this glowing at a point, called coronal discharge. And that represents the ionization of gas in the form of some kind of plasma. The final point that your book discusses is that I expect you to understand are the two ways to move charge. First way is very, very easy. This is the one that you use if you want to shock your roommate by rubbing your socks on a carpet floor. This is charging by friction, by actual contact. So you charge up your socks by rubbing them against a floor, and this is actual contact. Between the charges in an atom, in multiple atoms. Works really, really well in the winter because when it's very, very cold, charges flow much more nicely. The second form of charging is a little bit more obscure. It's called charging by induction. I would label this a sneaky way of charging. Because when you charge by induction, you don't actually have to touch two objects together. This is charge rearranged by close proximity. So let's understand, try to visualize what happens with induction. Let me say I'm a Greek guy and I'm walking around in my toga and I have my stick. And I take this little stick and I charge it up. I charge it up so that it's positively charged. And then I bring it up close to this sphere. And this sphere is neutrally charged. So it has some positive charges, but it also has an equal number of negative charges. I'm going to take this stick. I'm going to bring it really, really close to this neutral sphere. But I don't touch. Very important to note, in this step, they do not touch. I have my positively charged stick, and then I have my charges that are on my sphere. But my charges on my sphere are going to be affected by these positive charges. Any positive charges that are on this sphere are going to go running away. They're going to try to get as far away from that positive rod as they can. The negative charges, they're going to be quite sociable. Opposite charges attract, and they're all going to organize themselves close to this positive rod. Then what I can do is I can take this rod away. So let's get rid of my stick. Imagine we take this away. Okay. So once that is gone, I can then take a wire and hook it up into the ground. I'm gonna draw this little symbol here. We'll learn what this means later. This means ground. And what this does is it allows me to bring negative charges from the ground up to my sphere. So I have negative charges flowing in from the ground into this sphere. These negative charges are attracted to the positive charges, the large amount of positive charge that has been forced to kind of bundle up over on this one side. So negative charges from the ground are attracted and come onto the sphere. So now when I draw the charges on my sphere, after I disconnect this wire, all these negative charges have flown up and filled this guy with negative charge. It's still got its two little positive guys, still got two positive charges, But overall, it has more negative charges, so it's become negatively charged. And notice I charged this without any contact, without any touch. Charging by induction. And that, in a nutshell, is chapter 22.